So I have a little bonus video for you, and this is going to help explain a few things about simple harmonic motion that I didn't really cover in the other videos. It's a little bit more sophisticated mathematically, but at the same time it's very beautiful. So hopefully you can get something out of this. So what I want to start with is just remembering that the vertical motion in an oscillation that obeys simple harmonic motion is the same as the vertical motion of an object that's rotating around on a disk. Okay, so I want to kind of explain that in an interesting way. And while we're explaining that, we're also going to learn about the origin of these formulas for the kinetic energy and the potential energy of a spring. So the thing that I want to do is just imagine making a plot of the position of our object on the y-axis. So that shows the up and down motion. But then I'm going to add an x-axis, and what I'm going to plot on the x-axis is the velocity of our object. Okay. And so we'll just look through these various situations. And so we'll start in the first picture, and so there you have zero velocity. It's at the top, zero velocity, and we have the highest position. Okay, so I'm going to plot that at v equals 0 and position x, which is equal to, that'll be equal to the amplitude. And then the next one, it's gone down a little bit, and now the velocity is negative, and so that turns out to be over here. It's number 2. Number 3, it's gone down to the equilibrium position, which is x equals 0, and then the velocity is the maximum negative velocity that we're going to have. Number 4, we go back to a smaller downward velocity and then a smaller negative position still. And then number 5, the velocity is 0, so 0 on the x-axis, and on the y-axis we're at the lowest position. Okay, and so I can just then fill in the rest, 6, 7, 8, and then 9, we're back to the start. And if we filled in all the ones in between, what we would do is sweep out a path on this x and v plot that is just a circular path. Well, I should be a little bit careful. So we can't really compare, we can't really say that it's circular because the two axes have different units. And so in order to really be able to say, is something a circle on a graph, what we would mean is we want like this distance to be the same as this distance and the same as that distance and so forth. So that doesn't really make sense if the two axes have different units. But what I can do is make them have the same units by multiplying by some of our constants. So if instead I were to plot the square root of k times x and v times the square root of m, well, you can check that then both of the things that I'm plotting have units, weird units of the square root of kilograms times meters per second. And now it does make sense to ask whether the path is circular. And in fact, it turns out that on this graph with these units, you get an exactly circular path, and that the path is traversed at a constant rate. And so there's secretly actually this circular motion that is related to the simple harmonic motion, the up and down motion. If we keep track of both the position and the velocity, then you get this nice circular motion. Okay, and so one thing that is evident when you plot it this way is that well, what is special about a circle? What's special about a circle is that the radius is the same everywhere. The distance from the middle to the circle is the same everywhere. And so it's very interesting for us to express that mathematically. So if we say mathematically that the radius is the same everywhere, well, what is this distance? Here's r. So using Pythagoras' theorem, then we remember that the radius squared is equal to x distance squared plus the y distance squared. So this is the square root of kx squared plus the square root of m times v squared, and we learned that this is constant or unchanging in time. Wow, did I really just spell that? Constant. There we go. Okay, so this is unchanging in time. The fact that it's going around in a circle on this graph means that this combination of things is unchanging in time. And so let's just expand that out. So that gives me kx squared plus mv squared is constant. Okay, if I want, I could multiply that by a half, and I'm just going to do that because then we see something very familiar. So what we learned is that this combination of things, half kx squared plus half mv squared, is constant in time. And going back to our discussion of conservation laws, there was something that we expect to be constant in time for this oscillator, and that is the energy. Okay, so this expression that we just found is the energy. And so this kind of leads us to some understanding of why, for example, the kinetic energy is a half mv squared, or at least that it has the v squared in it instead of just v, and why the spring kinetic energy is half kx squared, or at least why it's x squared instead of, say, just x. Okay, so we've kind of, if you believe that the motion corresponds to going around on this circle at a uniform rate, then it follows immediately that there's this quantity that's conserved, and if you believe that this is the energy, then you learn that the kinetic energy must be some multiple of mv squared, and the potential energy is some multiple of kx squared. And this factor of a half is kind of just our choice for what we usually call the energy. So if you want even more, I will give you a little bit of a derivation of that fact. So far I just claimed that on this graph the motion was a circular motion at a constant rate, but I can actually prove that to you with not too much difficulty. So what I'm going to do is go back to our Newton's law that governs how everything moves. So we know that the rate of change of x is v, and the rate of change of v is, because it's f over m, which is minus k over m times x. But now I want to look at how these quantities change. So I will just adjust. So I'll go from these ones. So let me call that A, and I'll call that one B. Okay, so I'll just go from these rules to the rules for A and B. So we find that the rate of change of A turns out to be, you can check, the square root of k over m times b, and the rate of change of b equals minus the square root of k over m times a. So if you just plug in these definitions for A and for b into that, then you'll see that these two statements are just a rewriting of our statements from before. Okay, and so now we're basically ready to understand the picture above. And so it'll be helpful to think about this position A, B on the graph as a kind of a vector. Okay, actually, usually it would be written in this way, with the x coordinate first. And so we can actually draw a picture to show what these rules tell us. Okay, so if you translate these rules for the motion into a picture, okay, so if this is the point whose coordinates are b and a, and then I look at, well, the rate of change is this thing with square root of k over mb and minus the square root of k over ma. Well, that turns out to be, so we look at in what direction are these things changing, it turns out to be just exactly this perpendicular direction, and it turns out that the length or the magnitude of this change is the same everywhere on the circle. Okay, so if you start out at this point, and then, so that would be true at that point, but then if we're over here and you work out what is this rate of change, if I draw on the picture, how is it changing, then it always turns out to be, you can just try some examples of A and B. It always turns out to be just perpendicular. And so what that means is that you're always going to just be going in the direction that you're going, but then continuing around this circle. Okay. So just as an example, if you took like, just to show you a very explicit example, let's say I had this b equal to 1 and this is a equal to 0, and then we look at the rate of change of a, then it's root k over m times b, which is 1, and the rate of change of b would be 0. And so that says that we're going to be just going in this upward direction. So basically, the summary is these rules can be summarized on this picture by just saying that the direction that you're moving on the picture is always perpendicular to the line from this middle point to your current position. And that means that you will be going around the circle, and also the magnitude of this rate of change is always the same. So you end up going around the circle at a constant speed. So that was maybe a little bit detailed mathematically, but I just wanted to give you a sense that we can really prove these facts. It's all just the Newton's law equations that we started with, and those immediately kind of imply the fact that you go around on this circle on this xv plot at a constant rate. That implies that this combination, well, that the radius in that diagram is constant, and the physical interpretation of that radius is exactly what we call energy. And so we've actually just shown that this combination half kx squared plus half mv squared is actually conserved.